that in, okay, from thermo, okay? And now I want to tell you a little bit about what got me started on this. It's personal motivation. The question was, as I observed a disagreement between two eminent experimentalists, which of two temperature scales is better? Okay, how do we tell? That's not something that is covered anywhere in the literature, the courses, whatever. Okay. Now, my personal history of how I got into it is, first, I had lots of thermodynamics texts that I used to understand the subject because it bothered me. I used Callan's book, absolute classic, learned a great deal about the structure of thermodynamics, but Zippo, absolutely Zippo, about how you measure temperature in an operational sense. Okay? It was, very abstract. People say temperature and entropy are very abstract quantities, and they're absolutely right, but I will show you how to remove that abstractness. All right. And it occurred, after looking at the Callan book, and by the way, I began my education at Penn in 1960, a billion years ago, 65 years ago, guys, all right? Long time ago. But you know what? I'm still okay. The brain still works. Other parts still work, okay? So there's still life in this body. At any rate, okay, I studied Landau-Lifshitz. I studied Rife. I studied Fermi. All sorts of good stuff. Sorry, couldn't figure out temperature. But there was something in Landau and Lifshitz in statistical physics around page 50 on the absolute temperature scale, which was interesting, but I'll talk about it. Okay, we'll get to it and we'll see what's going on. And at any rate, what really hit me was at the 1972 Low Temperature Physics Conference in Boulder, Colorado. Okay, that's a long time ago, 53 years ago. I was asked to chair a session, okay, the session on low temperature thermometry. I am a theorist. I was a relative kid. I was just about to turn 30. What would I be able to do chairing that session? I could do nothing, and I didn't do anything, but I observed an interesting discussion, and this was confirmed for me by someone who was also there, whom I know, okay? And so that's how it started, okay? And basically, it was that there was a battle of thermometry, okay? For the helium-3 liquid-solid line down to the millikelvin range, and it was done by two people who were about to discover superfluidity in helium-3, the liquid phase, but they hadn't quite realized they were getting there. All right, they were just looking for it, but they didn't quite know what was going on. And the people were John Wheatley of La Jolla and Bob Richardson of Cornell. And Wheatley used noise thermometry. Richardson used Clausius-Clapeyron thermometry. I just want to comment. Clausius-Clapeyron thermometry is a thermometry that can only be done at the liquid-solid line. And it was first done in the context of ice and water. And it was a significant thing to have been done by Clapeyron in the, 1830s. But he didn't quite have it. The reason he didn't quite have it was that there was some quantity in the theory, the thermodynamic efficiency, okay, as a function of temperature, whatever temperature was. He didn't know that. Clausius came along later. He knew what temperature was, and so he completed the job. So that's why it's Clausius-Clapeyron instead of just Clapeyron. All right. All right. Now, the difference between these two thermometries has to do with the difference between the two, in part to with the difference between the two types of thermometry. Noise thermometry involves statistical reasoning. Clausius-Clapeyron thermometry involves thermodynamics. There is a difference, okay? And I'm going to talk to you about that right now, because here I'm going to talk to you briefly about the general theory of thermometry. If you use thermodynamics, you specify some temperature, T star, all right? That is the beginning of your procedure. You've got to specify it somewhere and then find the temperature elsewhere in the PV plane. But if you use statistical physics, then the temperature scale is determined by the Boltzmann constant, KB, or the mechanical equivalent of heat. It's built into KB and the mechanical equivalent of heat are built into one another. So we have that number, okay? And we need that. Now, I will then talk about specific statistical mechanical methods, equilibrium properties, equilibrium fluctuations, and near equilibrium fluctuations. But let me get to the heart of the matter right away. I'm going to sit down, I'm going to get relaxed if I can, and I'm going to talk about basic thermodynamics, okay? So the first thing I'm going to do is I'm going to draw the PV plane, all right? And I'm going to pick some point, P star, B star, and I'm going to say that at that point, I know the temperature, okay? We choose it for our temperature scale. Once we get that value, the game is over, okay? We can figure out for some region what the temperature is. Now, there are, as far as I know, Clausius-Clapeyron is based on thermodynamics. There's the general approach that I'm going to show you now, and there's another one that involves entropy minimization, okay, for getting temperature using the thermodynamic theory. But they all involve picking a temperature. Whereas the theories that depend upon statistical mechanical methods do not specify a temperature. All right, so let's go to it. First, let's remind ourselves that temperature is a function of pressure and volume. We know about the ideal gas. We're not going to need that, but just that's an example, okay? PV equals nRT, whatever. All right, so here we go. Now temperature is abstract. What is temperature? Well, I want to do the following. I want dt. dt is equal to dt dv. Let me do it. dt dp, the constant v times dp, and dt dv, a constant p times dv. Now, that has not really gotten us anything. Let me just go a little bit further, though. I don't like working with dt because it depends on your temperature scale. Let's just make it dt over t, okay? And you can say, what did this buy us? And so far, nothing. But now we're going to use the magic of some Maxwell relations, okay? And the Maxwell relations are going to involve the Helmholtz free energy. I'm going to use Fe, which is given by F, which is equal to the energy minus T times S. And you are going to say, what good is that? Okay, I want to write down the dF, though. dF is equal to, okay, dE is, as every child knows, TdS minus PdV. If you have this differential with a negative sign from dF, you're going to subtract off the TdS term, and you're going to have an additional minus SdT term. Okay, here we go.